Hello, it's Chem Interview. Here we talk to the most prominent representatives of chemical science and industry. And today our guest is the truly legendary scientist, one of the most famous organic chemists in the world, who is among the 100 most cited chemists, Kendall Houk. Hello, Professor Houk. Thank you for coming. Since we have a very wide and diverse audience, let me ask you first to briefly introduce yourself and tell us what you mainly do as a scientist.
Okay. Thank you for this opportunity. Happy to talk with you. My name is Kendall Houk, but my friends call me Ken, and I publish by the initials KN. Those are all me. And I'm an organic chemist, although I'm started as an experimental organic chemist and gradually evolved into a computational chemist. So nowadays I do only computation, but collaborate frequently with experimentalists. So my main goal in life then is to try to help understand experimental results and to provide guidance for future chemistry. I'm a professor at UCLA, but I've been a professor at other places before. I was a student at Harvard, then I went to Louisiana State University and then the University of Pittsburgh. And I also spent some time at the National Science Foundation as the director of the chemistry division for 2 years. So that is who I am.
Let's probably start with your childhood. In your previous interviews, you said that you have had a passion for science since childhood. What was the reason for choosing chemistry as your professional path?
Yeah, so I was interested, I'm not sure exactly why, but in science from grade school. I remember having science projects in 7th and 8th grade and in high school. And what I wanted to do then was be an inventor. So that's kind of what we call people like Thomas Edison and Henry Ford, people who develop cool things and not necessarily scientists. But then when I went to college to Harvard, by that time, I definitely knew I wanted to be either a chemist or a physicist. I was probably a little more interested in physics, but the competition and in physics classes at Harvard was pretty fierce. And maybe that's the reason, or because I really like to do experiments, that I quickly gravitated to chemistry. So from the early time in college, I was determined to be a chemist, and I've just done that ever since.
That's interesting. And as far as I know, you started out as a synthetic chemist, as an experimentalist, and then smoothly moved on to computation, which is not so typical in our time because now people decide directly. Okay, here is computational chemistry, and here is theoretical chemistry. I would like to know what caused your decision, this switch from experiments to calculations.
Well, it's all somewhat accidental. As an undergraduate, I started doing research with a professor named Roy Olofsson. He was a young guy at Harvard who had worked with Woodward, and that was synthetic. I was working on synthesis of heterocycles, and my first paper is from that era. And then probably because of his influence, when I look back on it, it's because I worked for him that everything that's happened to me has happened. I ended up working for Woodward as a graduate student, probably because of my undergraduate advisor's influence. And then Woodward was just entering into the orbital symmetry era. So I joined his group fully expecting to do synthesis, but the project that I eventually worked on that he gave me after several very complicated synthetic choices that I didn't think were very feasible, he suggested I look for a 6+4 cycloaddition. So this was inspired by prediction by Woodward and Hoffman that this reaction should happen. But there weren't any examples. So that was a pretty cool project. I could take any triene and any diene and study the reaction. And eventually I found some that gave 6+4 cycloadditions. And then when I started as an assistant professor at Louisiana State University. This just happened to be the time that computations were taking off. Computers existed, but the programs that existed were semi-empirical or empirical, like extended Huckel and CNDO, it was called, one of the simple semi-empirical methods. And I actually had some undergraduates who came to me and wanted to do something on computers. So I had them start to calculate some orbitals of molecules that I was interested in studying experimentally. So my experimental program was to study cycloadditions of highly conjugated systems and try to understand what controls which products are favored. And so we did some simple MO calculations to do that. And then Gaussian 70 came out, and it became suddenly possible to do ab initio calculations, even if you weren't a computational chemist. So I started to learn that. Plus, I had colleagues at Louisiana State who were eager to answer my questions about quantum mechanics. And so I just happened to be starting my career at a time when computational chemistry was really beginning to take off. I just followed that wave up as it progressed, and that's why I've ended up where I have. But it's all accidental. I never planned any of this.
What is the purpose of the existence of computational and organic computational chemistry? Why do we need it? Because of course we can do synthesis and spectroscopy and observe different things, and nowadays spectroscopy is very accurate, so we can measure very small scales of time. So why do we need professional chemists for that?
Yeah, well, that's an interesting question, and I think it's because one gets such a additional level of understanding from computation that isn't really directly possible by experiment. Experiment, of course, is the heart of chemistry. There isn't really, without the reality of experiments, it's not so interesting. It becomes physics or mathematics. But what one learns from computations is the details of how reactions happen or of what the structures of molecules are. Of course, spectroscopy and especially X-ray crystallography and electron crystallography now can give the structure, that is the positions of atoms in the most stable complex. But from computations, you can learn the details of bonding, what exactly is holding the atoms together and makes different positions reactive, for example. And furthermore, for reactions, you can really delve into understanding the details of electronic structure and how that leads to a specific reaction path. Because for complicated molecules, there are always a huge number of possible reactions. A question is that if we really understand chemistry, then we can understand why one particular pathway happens instead of another. So I'm especially interested in reactivity. That's why I keep talking about reactions. But of course, in structure is the same thing. You can get a three-dimensional structure experimentally, but you can't necessarily understand why that structure, as opposed to many other possible connectivities, is the best one.
One of the areas of research is the enzyme catalyzed reactions. How do you think such catalysis could be used in the future? Not in academics for studying purposes, but rather for industrial purposes.
Yeah, so I think it's really becoming more and more important. We've had collaborations with a company called Codexis, and Codexis is also very involved with Merck. And Merck and other pharmaceutical companies are building significant biocatalysis groups. And the reason is because one can develop enzymes to carry out some fairly complex transformations and to do it very efficiently without using transition metal catalysts or actually having any significant byproducts. So I believe that that's going to become increasingly important. And of course, it's been acknowledged by the Nobel Prize to Francis Arnold, but the idea of directed evolution to create enzymes that do reactions that aren't done by natural enzymes really demonstrates a great potential for that in the future.
Now I would have a rather personal question to you. In some of your interviews, you mentioned that you actually like doing sports and you do it on purpose. What's your favorite sport and why do you do it?
Well, yeah, I've always been interested in sports. Just as a kid, just playing baseball, especially as an American kid sport. It was before soccer ever was played in the U.S. I suppose I kicked the ball around a little bit, but so baseball was my strong interest. I played basketball too, but I'm too short to be very good at that. And tennis. So tennis and baseball were probably my principal young sports. But then when I got older, middle age, let's say, I got into running, in part because I smoked as a youngster. Everybody smoked in the early days. And Woodward was famous for smoking during lectures, and so I quit smoking about the time I came to UCLA and started running. And then I got really into it and started running marathons. And so I ran 10 marathons and then eventually kind of wore my back out. So I didn't run much anymore, although run shorter distances. And tennis and racquetball and squash were my other sports. But somehow when I got into running, that took all of my time. So I don't really play those much anymore. I've been interested in sports just, for playing games, but now I think it's really a critical thing in keeping mental health and, staying physically fit also, but it's really very important. I've become kind of addicted to walking or running or biking at this stage because it really, additionally, I do workouts in the gym, I do weight training and so forth. But all of these things I think really are very important for mental health and for brain clarity. I always feel more alert and creative, if you like, after exercising. So my goal now is to always exercise in the morning before I come to work. And I've kept that up pretty well. I also like just the spectator sports. Probably American football is probably my favorite, but basketball and I watch tennis and basketball and football, baseball some, but mostly just when they get to the championship games. There's so many games now that you could spend all your time watching, but they get really exciting when it becomes near championship time.
And if you could choose some other profession instead of being a scientist, what could it be?
Yeah. Well, I did think about other things when I was young, and most of them have to do with art or architecture. So I was a very avid trumpet player in my days right through college and graduate school. I played in jazz groups and in concert bands and orchestras. And I thought for a while about becoming a professional musician, but I especially wanted to be a jazz musician. But I observed the successful jazz musicians and the life that they went through, and it looked like a difficult life. First of all, it's hard to become very famous as a jazz musician. And even if you do, a lot of them ended up as like drug addicts and stuff. So it seemed like it wasn't such a great profession. During college, I thought for 1 year, I thought about becoming an architect instead. And I've always been interested in art and music. So I still am very eager to go to art museums and symphony concerts. I go to the Los Angeles Philharmonic regularly. And so if I were to be anything else, musician was the thing I was good enough at that I could have been a professional musician. Artist, I'm not really good enough to be a professional artist, but I would find that life interesting. An architect might be something in between, it's very scientific and mathematical, but is creative as well.
Since we're talking about music, it's really interesting because I have now two questions in my mind. First, what is your favorite genre in music? And the second one is, recently we have spoken to Professor Karel from the LMU University in Munich, and once he said that as a scientist you have rock and roll every day. So do you think scientists have rock and roll every day, or they rather have some other kind of music every day?
Well, in terms of music, in terms of jazz, I'm a little dated because my favorite jazz musicians are still people who were really active maybe 50 years ago. So Miles Davis is my main hero, but there have been some other modern trumpet players that I've followed closely, but I'd still say Miles Davis is my hero, the person I've tried to emulate when I play. And incidentally, I play again due to the pandemic. I got my trumpet out after 50 years and started playing again. It took a lot of effort to get the lip going again, but I can play a lot of things now. But I also like concert orchestra, LA Philharmonic. I go about a dozen times a year, and but my taste in music is very broad. I like jazz. I like rock and roll. I like symphony, the classics, and so I think that I can see what Karel said. Certainly, there is a similarity between the creativity and in science, and especially in the kind of chemistry that we do, and trying to figure out new reactions, understand how old reactions happen, but then figure out new ones that could be done instead and understand the details of those. That is in some ways like jazz in the sense of improvisation and trying to create something on the spot that's new and interesting.
Well, maybe that's why so many scientists like music. And I even think that probably those who are playing a musical instrument, perhaps it helps the brain to develop some other abilities compared to mathematics or chemistry or any other kind of science. Another question is also related to your current topic of the research. Several years ago, scientists received the Nobel Prize for molecular machines, and the recent 35-40 years, supramolecular chemistry became really famous. And it is also quite an extensive area of research right now. You're also performing some calculations in the molecular machines. Why did you choose them? And why did you believe there is a certain research interest in it?
Yeah, so like much of my research, it came from collaborations. First with Donald Cram, who won the Nobel Prize for his host-guest chemistry work. And we were colleagues. His office was right next door to mine when I moved to UCLA. And so he basically understood his chemistry using space-filling models, so-called CPK models. Corey Pauling Coltoun. These are plastic models that have the shapes. The atoms are roughly proportional to the size of different atoms. And he built big molecules out of these models and tried to understand what molecules could fit inside others and develop the concept of container molecules. But he also did some interesting experiments where he measured the rates of small molecules, guest molecules, getting in and out of hosts. And so our first collaborations in this area was really doing calculations to try to understand what was actually occurring. And we discovered the concept of gating, which had to do with parts of the molecules opening and closing, allowing guests to get in and out. So that was really the first thing. Then when he retired, we hired Fraser Stoddard as his replacement. And Fraser Stoddard, of course, was a pioneer and one of the Nobel laureates for molecular machines. And he was interested in understanding in more detail the kinds of forces that were important for his molecules. And he was really pioneer in so-called mechanochemistry. So we did calculations on his systems then, so-called rotexanes, trying to understand the energies for slipping of the outer parts of the molecule around the inner parts. And then beyond that, the collaborations have been with my colleague, Miguel Garcia Garibay, and he's into real molecular machines. So measuring motions of parts of solid state devices. And we do calculations on molecular dynamics and quantum mechanics on the energetics of these kinds of processes. So I must admit, it's not my creative mind, it's the minds of my collaborators that have led us to the projects that we've worked on in nanochemistry or this kind of molecular machine area.